Hi everyone, today a video in the energetics series looking at bond enthalpies. So if you were to plot the enthalpy change of combustion of some straight chain alkanes against the number of carbon atoms, so on the y-axis we have our enthalpy change of combustion, the x-axis the number of carbon atoms we have, so that's for example going from methane to ethane to propane to butane, so 1, 2, 3, 4, etc. on the x-axis, you get a straight line. Now each alkane differs from the previous one by just one CH2 group. So this is one extra carbon-carbon bond and two extra carbon-hydrogen bonds. And so because it's a straight line, there's this the same difference in one CH2 group per alkane difference, and there's actually the same constant change in the enthalpy change of combustion. And so it suggests that you can assign a definite amount of energy to a particular bond. Now remember, we have to put in energy to break a covalent bond. We have to put in energy to break it, and that's an endothermic change. We've had to take energy in from our surroundings to break a bond. Therefore, it's a positive delta H, a positive enthalpy change, and therefore it's endothermic. And so we can define something called the bond dissociation enthalpy, literally the enthalpy to dissociate, to break a bond. It's defined as the enthalpy change required to break a covalent bond with all of the species in the gaseous state. And the two really key bits of this here I've highlighted in red. So the key thing is that it's to break a covalent bond. You'll never see a bond dissociation enthalpy for a metallic bond or for an ionic bond. It has to be a covalent bond, and the species must be in the gaseous state. So it's like thinking about the equations and the definitions for ionization energy. They're all gaseous. Same thing with bond dissociation enthalpy. Everything has to be in the gaseous state. Now, if we have a bond that we're breaking, that's our endothermic change. We have to take energy in to do that. But if the same bond forms, well then we have energy given out. It's an exothermic change. And it's the same amount of energy. So if I have a CH bond being broken, the amount of energy that we've taken in would be exactly the same as if I made my CH bond and the energy was released. However, the same bond, say for example a carbon-carbon bond, might have slightly different bond enthalpies in different molecules. And this is just due to the fact that in different molecules, you have slightly different environments for that carbon-carbon bond, maybe different functional groups or different lengths or something. It's just that every single bond isn't in exactly the same environment, essentially, and so there's very slight differences in the actual bond enthalpies in different molecules. So because there's normally slight differences depending on the type of molecule we're in, the kind of functional groups we have, etc., we usually use something called the mean bond enthalpy. So this is the average of all these values for a particular bond. The mean bond enthalpy, literally the average bond enthalpy. And this is defined as the enthalpy change required to break a covalent bond with all of the species in the gaseous state averaged over a range of compounds. So it's basically the same definition we had for our bond enthalpy, the enthalpy change to break a covalent bond, not an ionic or a metallic, a covalent bond, everything in the gaseous state. But now we have this extra bit that everything is averaged over a range of compounds. And as we said on the previous slide, we always give out the same amount of energy when we form a certain bond as when that same bond is broken and we take the energy in. Actuality, this is an application of Hess's law. It's the idea that we can't create or destroy energy, our first principle of thermodynamics. Now, since mean bond enthalpies are averages, if we use them for calculations on a specific compound, it will only give us the approximate answer. So because the actual specific bond enthalpy in that molecule will have a specific value, because we're using the average, we might be slightly off. So we might have a slight discrepancy between our experimental value and the value that we theoretically calculate using these mean bond enthalpies, because they are averages. And all mean bond enthalpies are positive, endothermic, because again, we have to put energy in to break bonds. So, for example, the hydrogen-hydrogen bond energy is the energy required to break the covalent bond of the hydrogen in the gaseous state to produce separate gaseous hydrogen atoms. So we can write that equation as H2 as a gas, dissociating to form two lots of H as a gas as well. And you can see there that our delta H for this, our mean bond enthalpy essentially for this, is plus 436 kilojoules per mole, an endothermic value. The CH mean bond enthalpy is the energy required to break the covalent bond to produce separate gaseous atoms averaged over a range of compounds. So notice the difference between this and the hydrogen example. Our bond energy is just the energy required to break the covalent bond of all the gaseous species. The CH mean bond enthalpy is the energy required to break the covalent bond to produce the gaseous atoms from the starting gaseous molecule, averaged over a range of compounds. So for example, we could think about methane, CH4, and we could think about breaking that molecule, potentially literally breaking every bond in that, and we'd have 4 CH bonds to break. And in doing that, we'd have gaseous methane breaking up to form 4 lots of hydrogen atoms that are gaseous and carbon as a gas. Now, that overall enthalpy change to break all 4 CH bonds in the gaseous state comes out to be plus 1,664 kilojoules per mole. However, we're looking for the mean bond enthalpy of the CH bond, so it's actually a quarter of the energy to break it, because we're looking for how much it takes to break 1 CH bond. Our actual enthalpy change for that reaction is breaking 4 CH bonds. So we have to divide by 4. So the mean bond enthalpy for the CH bond is 460 kilojoules per mole. So it's kind of similar to our definitions of enthalpy change of formation and enthalpy change of combustion that we've seen in previous videos, that it always referred to 1 mole. For mean bond enthalpies, it might be that we have multiple of the same bond in our compound. We're interested only in one of those bonds though. So if we have in this case 4 of the same bond being broken, we need to divide by 4 to work out simply what the mean bond enthalpy is one of those bonds is. So how do we use mean bond enthalpies to calculate enthalpy changes? The easiest way to do it is to simply remember the mnemonic burp. So our overall enthalpy change, when we're given bond enthalpies as our data, is simply the sum of the mean bond enthalpies of the reactants minus the sum of the mean bond enthalpies of the products. So we calculate what the total mean bond enthalpies of the reactants are, just add them all together. We calculate what the mean bond enthalpies of all the products are, add them all together. And then we do the reactants sum minus the products sum. So if you're given bond enthalpy data, reactants minus products, burp. So an actual example of a calculation. Let's say we have this reaction here. So ethane, C2H6, reacting with Cl2 as a gas. Remember that everything is a gas here. The ethane is a gas as well because we're mean bond enthalpies. We think back to our definition. It's a gaseous species. And this forms the chloroethane, C2H5Cl, gas, plus HCl as a gas. This is an example of a free radical substitution reaction. Now, I would say the easiest thing to do when you're doing calculations using mean bond enthalpies is to draw out the full displayed formula of every single species that you have in your equation. And the reason we're going to draw out every single bond, and the full display, remember the full displayed formula means drawing out every bond, is so that we can see which bonds break, and we can also see how many of each bond we have. And so there's 2 ways to go about doing this calculation. The first is you can consider actually only the bonds that break. So if we look at our ethane molecule, we have 1 carbon-carbon bond and 6 carbon-hydrogen bonds. Our Cl molecule has a chlorine-chlorine bond. If we then look at our chloroethane, we still have our carbon-carbon single bond. We still have 5 carbon-hydrogen bonds that have been untouched. It's only that carbon-hydrogen bond at the end that's been touched and changed into a carbon-chlorine bond. Likewise, our Cl-Cl bond has been broken and turned into an HCl bond. So one way to do it is to simply just consider, ignoring the mean bond enthalpies, for example, of those 5 carbon-hydrogen bonds and of the carbon-carbon single bond, because they're unchanged, and just considering the bonds that have been made and broken. That leads to a simpler calculation. However, I would recommend calculating it for every single bond, because you're much more likely to make a mistake in trying to figure out which bonds have broken and which bonds have been made. It's much easier to simply just consider every bond being broken, every bond being formed. You're much less likely to make a mistake doing it this way. And so if we consider every single bond, as I said, we have 6 CH bonds. And so we take our mean bond enthalpy, which is 413 kilojoules per mole, and times it by 6. We have 1 CC bond, 1 chlorine-chlorine bond. We add all these together, and the sum for our reactants comes out to be 3,068 kilojoules per mole. We can then do the same for the product side. Here we have 5 CH bonds, 1 CC bond, 1 carbon-chlorine bond, and 1 hydrogen-chlorine bond. So literally just say what you see. Add all those together, and what we end up with is 3,190 kilojoules per mole. And then remember our numeric, burp, bond enthalpy values means we do reactants minus products. So we do the 3068 minus the 3190, and we end up here with an overall enthalpy change of reaction as being negative 122 kilojoules per mole. So always draw out the full displayed formula. Don't try and do it just from the stoichiometric equation at the top, because you're very likely to forget certain bonds. Always draw out the full displayed formulae, and I would always recommend doing it as recommending every single bond being broken, every single bond being formed. Now, the answers that we obtain when we use thermochemical cycles to calculate enthalpy changes of reaction, that's using the Hess's cycles that we've talked about in the previous video, when we use formation and combustion enthalpy datas, these are actually the correct answers. The answers that we get by using these mean bond enthalpy data, they're only approximate values. Because as we said, the mean bond enthalpy values, it's literally in the name, they are averages, they're the mean of all of the compounds that that bond is in. It's taken from a range of compounds. Whereas in a specific compound, the one we're dealing with to calculate our enthalpy change of reaction, a bond will have a specific value for its enthalpy. So this is where we get our difference here between our theoretical value that we calculate using the mean bond enthalpies and our real value that essentially we can do a few experiments and then do a Hess's law cycle to work out what it is as well. And so for that ethane plus Cl2 reaction we've just seen on the previous slide, when using mean bond enthalpies, we get negative 122 kilojoules per mole. So that's using the mean bond enthalpies, the average over a range of compounds of all those bonds. Actually using a thermochemical cycle, using Hess's law and combustion or formation data, you end up with an enthalpy change of negative 144 kilojoules per mole. And so, while it's not the biggest difference in the world, you can see that there is actually a difference between those numbers. And the thermochemical cycle, the Hess's law that we use with our formation data, these are the correct answers, because the formation values used are obtained from the actual specific compounds involved. They're not an average across a range of compounds, they're from the actual specific compounds involved. So sometimes a question will ask you to calculate mean bond enthalpies, it will then actually give you what the true answer is and ask you why it's different. It's because you've used mean bond enthalpies averaged over a range of compounds, not for the specific compounds in the question. However, you might be wondering, well, why use mean bond enthalpies at all? They allow us to calculate approximate enthalpy change values, and this would be very useful, for example, if actually calculating the enthalpy change would be a very laborious process. It would take many experiments. It would be very difficult to do. Potentially a compound that has never actually been made before, we can calculate it to see if it's theoretically feasible, possible or not. Or for a reaction that would just simply be impossible to carry out in a certain way. So they do have their uses. But as we said, they're not always reliable. So they can give us our rough estimate as to which bond might be the most likely to break in a reaction based simply on how strong the bonds are. You typically expect the weakest bond to be the one that breaks. However, we're assuming a number of things. The first thing is, going back to our definition, everything takes place in the gas phase because everything has to be gaseous. Now in reality, most reactions don't take place in the gas phase. Most of them take place in solution. And so this ignores any interactions that we have really between our molecules, any interactions that we have between the molecules and the solvents, any solvent effects. There's lots and lots of other thermodynamic effects that we are ignoring. It also ignores potentially any polarity of the bond. So while we may have a particularly strong bond, it could be actually a very polar bond. So for example, the carbon-chlorine bond is a fairly strong bond. It's also very polar and so reactive. And so therefore, if you were doing your calculations, you might expect a weaker bond on thermodynamic data to actually break first, when in reality it might be the carbon-chlorine bond because it's more reactive, because it's more polar. It also assumes that the bonds break in a homolytic fashion. Now, what we mean by that is that if the bonds are to break, they go evenly. So one electron goes to each atom. So what this means is, let's say we have an OH bond that breaks. We're assuming this homolytic fission, one electron to each, that one electron goes onto the oxygen, one electron goes onto the hydrogen. So essentially we're forming radical species with unpaired electrons, O radical and H radical. That's our homolytic cleavage. However, we know that typically if we break an OH bond, it's very rare that we're going to end up with an oxygen radical and a hydrogen radical. What's much more likely is for it to break into an O- anion an H plus cation. This is what we call heterolytic cleavage, or heterolytic breaking of the bond, where both electrons move onto one of those atoms in the bond. And so in this case, both of our electrons from that OH bond have moved onto the oxygen atom. The oxygen's more electronegative, that makes sense, it's happy to gain those electrons. And so we have an O- anion and an H plus cation. So it ignores the fact that maybe a lot of the bonds that break won't necessarily break homolytically, but will break heterolytically. So time to have a go at an example for yourself. If you want to have a go, pause the video and the answers will be on the next slide. So the question we had here was about the combustion of propene. So we had C3H6 being reacted with oxygen, O2, to produce our combustion products of carbon dioxide, CO2, and water. And remember that the state symbols weren't in the question, but for this to be true, for using mean bond enthalpies, we would have to be doing this in the gas state. So all of these species would be gaseous. And again, remember that that's one of our potential drawbacks of using mean bond enthalpies. So the first thing that I'm going to do here, as I said, is to draw out the full displayed formula, so draw out every single bond. And again, I'm going to do my calculation assuming that every bond breaks and every bond reforms, essentially. So, look at our reactants, our left-hand side. We have one carbon-carbon single bond, we have one carbon-carbon double bond, and we have 6 carbon-hydrogen single bonds. So we then look at our mean bond enthalpy data table. We have 348 for the carbon-carbon single bond, 612 for the carbon-carbon double bond, and then 6 times 412 for the carbon-hydrogen single bonds to make 2,472 for that. We then have 4.5 lots of our oxygen-oxygen double bond. So again, it's really, really important to make sure that our equations are balanced. In the question, it was already balanced for us, but if it wasn't already balanced, make sure you balance your equation, because you need to know the mole ratios to be able to calculate these values correctly. And so summing together all of those reactants, we end up with 5,664 kilojoules per mole. Then looking at the product side, if we look at our CO2 molecule, we have 2 carbon-oxygen double bonds. But we have 3 moles of CO2. So we actually have 3 lots of the 2 CO double bonds, and so we have 6 CO double bonds. That's 6 times 743. Likewise, in our water molecule, we have 2 OH bonds, but we have 3 lots of them, so we have 6 OH single bonds, which is 6 times 463. And adding those together, our products come out to be 7,236 kilojoules per mole. Then remember the mnemonic that if we have bond enthalpy data, it's BERP, so reactants minus products. So the sum of the reactants minus the sum of the products gives us our standard, in this case, a standard enthalpy change of combustion. And if we do that sum, the 5,664 minus the 7,236, it comes out to be negative 1,572. So that's what we'd expect for a combustion reaction, exothermic and also quite heavily exothermic as well. So as I've said before, generally in these kind of questions, always make sure the equation's balanced for a start, and then always draw everything out in the full displayed formula, and I recommend writing out every single bond enthalpy. So not just the bonds that are actually made and broken and actually change, but every single bond. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check those pages if you're interested in that. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.